Hey guys, Jackie here. Today I'm gonna show you the use of the Open VSP Arrow. So it's a low fidelity computational method that can analyze the aerodynamic performance of your aircraft. It's a really cool function that's built in the Open VSP. So I think it's really good method to see how your airplane performs on a low fidelity aspect. So first thing first, I would recommend you to go to the OpenVSP wiki. So you can just Google search it and you found their website. So this is their general documentation website, which has a lot of tutorial and then also the documentation file for the OpenVSP and the VSP Arrow. So when you go to their main website, go to the guides to engineering analysis with OpenVSP. Okay, so it has the VSP Arrow intro and then also the parasitic drag tools intro. So when you go in there, you have the VSP Arrow tutorials in there. It will tell you again how to use it from step to step. Their version might be a little bit old, so it might not match what you have in your latest version, but the general idea is the same. Okay, so you can read through the file if you want, and it also have the all these values, what values stands for what in the output file, so you can use them as a reference in the future. Okay, so now let's go back to the OpenVSP. So in the OpenVSP, when you load your model in here, one thing I would recommend it for a OpenVSP Arrow analysis is to delete your propeller. Okay, I think the OpenVSP does not like propeller model in there. Anything you think it's a weird shape, you can delete it, but you can keep your, say, the engine nacelle in there for the drag calculation. Your vertical tail and horizontal tail in there. Everything else can be in there. Landing gear could be there, but I just recommended not to keep the propeller. So the first analysis we can do is the parasitic drag analysis, which is a really cool features that the OpenVSP has to analyze your parasitic drag. So again, in their documentations, I believe they have the parasitic drag tool run through. Actually, run through you how to use everything, what equation they use, and everything else, which is really, really cool. All the different equations you can calculate the skiing friction coefficient, and then what they use. So it's a really cool document you can look through. Okay, so go back here on the parasitic drag window here. You want to first thing make sure your model length unit is correct. If you're using a SI unit or a metrics unit, you want to make sure you use the right unit. I'm using feet to build up my models. It's fine. The laminar and turbulence skiing friction coefficient equations, you can just use the default unless you are doing a supersonic aircraft. SREF you can use from model, which what we usually use is the projected area of your wings. Either you know that value, you can just simply get it from the model. Okay, and then you know your flight condition here. So I know my airplane is going to fly at 100 knots, which is 168 feet per minute at 1,000 feet altitude. And then the temperature, let's just give it a nice 70 Fahrenheit. Okay, use the standard atmosphere model for the calculation. But that's all the input you need. Okay, you just simply click calculate CD naught. It will run and it will give you the value for CD naught. And you can always export this file to a CSV file so these values will be saved. So on this table here, we actually get the wetted area for each component of your airplane, which is really cool. And then here's the FF value, which is the foam factor. Okay, so in their documentation, the foam factor actually is a value that's represent the streamline or like the how streamlined your body is. Okay, if you see the plot here, on the x-axis is the thickness to core ratio, and on the y-axis the foam factor. You see, with the increment in your thickness to core ratio, you have a higher foam factor, which means the higher the foam factor, the less streamlined body you are. Okay, so that's just something represented the streamlinedness kind of performance of each component of your airplane. And that's the FF value. The CD value, that's your component drag coefficient, the parasitic drag coefficient with respect to the SREF being input. And it also tells you how many percentage it actually contributes to the total drag, which is pretty cool. Okay, so this will be a tool for a reference to compare the value you got from here to the values that you actually calculate from your arrows assignment using all those equations from different textbooks. And this is, you can compare, say, hey, I get this value from the OpenVSP and I get this values from the textbook. Whether these values match or not, whether they make sense or not, you can justify it, put them together, and then you can always say, hey, I trust this more than that, and my reason is what. Okay, so that will be the parasitic drag toolbox. So if we go to the VSPAero toolbox here, we can open the VSPAero box here. But before that, we want to make sure you actually have the right airfoil built into your model. So going to your wing thing is first is to look at your wing, because the VSPAero we're going to use is running based on the vortex lattice method. So you want to have enough panel, enough vortex lines in your model. So if your wing only have one subsections, which is kind of common, I would recommend you to split it into 5 different sections. So first thing is you go into your wing in the sections. If you have less than 5, just select random sections, or couple sections that has really high span value, to split them so you have enough a vortex lines for your analysis. You have a nice distribution of your wing. Okay, and then in the airfoil here, so again, I mentioned in the previous video they have different airfoil in there. Okay, however, if your airplane has a very special airfoil, you can always go back to the folder, go to the airfoiltools.com. You can download the Celic type data file in there, and either save it as a .af file or save it as a .dat file. I would recommend it using saving everything as a .af file. Okay, so if you open the .af file using the notepad, it's the same format that you have from the airfoiltools.com. So just saving these airfoil coordinates, it will save it in there. So these will be used by OpenVSP. Actually, the airfoil analysis it used is based on the Xfoil. Okay, so it takes similar as XFLR5 to do the analysis. So if you have a special airfoil, go ahead, save everything as a .af file or .dat file in the airfoil folder in OpenVSP. And if you want to load them in here in your wing section here, go select AF file. Okay, I go in there, and then you just say read file and select whatever the DAT file or the AF file in there. You actually load them in there. Okay, you just load it. It'll give you the value, I think. I think you have to save it as a airfoil file. There we go. Yeah. So save everything as a .af file, and then you can have it in there, or change your airfoil. Okay. But now let's go back to my airfoil. So it's the 63015. Just make sure it's right. Okay. And then we're going back to the VSPAero here. Okay. So in the overview here, we want to use the VLM method. Okay. And then the VLM method doesn't like fuselage. So what I usually recommend to do is to hide your fuselage, select no show. Okay, we'll hide your fuselage. And then the setting here, in the VSPAero setting here, just to the geometry set using the shown. Okay, so whatever is not shown won't be calculated. Okay, and then you can actually, again, automatically set in your reference area. Okay, and if you want to calculate the right moment arm, pitching moment coefficient, as you know in your CG from your weight homework, you can put it in there. Okay, again, your reference point is from your nose, so putting the right CG location as your reference. Okay, on here you can have your angle of attack starting point and ending point. I would recommend doing about 10 or 15 to -15 to 15 degree with an increment of 1 degree. So this is actually points here, okay? So if I do a 1 to 10 degree with the 4 points in there, it's actually like increment of 3. So if you want to do negative 10 to 10 degree with increment of 1, you want to put in 21 points in here, okay? In the advanced here, you want to select, the maximum available CPU you have, so it does really quick. In the wake iteration here, I would recommend it at least 6 iterations will give you a pretty good results for the sake of time saving. Here, I'm just gonna use 3 iterations. And then in the rotor here, you're gonna put in your free stream velocity for cruise condition and your air density. Okay, again, gonna use consistent unit. If your model is built in the English unit, you want to use the right units, okay? If you set everything else done, you click the launch solver, it'll start to solve, and it will give you the result messenger, okay? So this is what you want to gonna get after you finish your analysis, okay? The convergence history, you don't need to worry about it, okay? On the load distribution here, so we can actually see the lift and drag distribution in your plot. So be aware of they will actually plotting, all the angle of attack you tested. Okay, if we focus on one angle of attack here, it might give you the lift coefficient of this specific section. Okay, and if you multiply this value and divide by the average chord or mean aerodynamic core value, you will get your lift distribution. So that's your CL lift coefficient distribution. This is your lift distribution. Okay, so they are different. Okay, you can also have other parameters that you want to plot, okay, and you can plot multiple angle of attack in there. In the sweep here, we can actually plot other stuff, okay, that's your drag polar. I don't have a lot of data points, so my drag polar looks weird. You can actually change your X and Y axis value. I can change X to the angle of attack, Y to my lift coefficient, that's my lift curve slope, and then I can have my, drag value here, okay, for the whole, horizontal tail and wing, the drag value. You can always export these data to a CSV file. So if you click export to CSV here, okay, I'm gonna go ahead do a aero.csv. I'm gonna export it there. And then if I open the CSV file that's just generated, the file is somehow a little bit messy. But I will run you through on what's each values here. You can always reference back to their website if you have any questions on other issues, okay? So the first thing that we will show here is the calculation of each angle of attack value as a whole airplane, okay? So that's what you see in the plot here in your sweep. So the result manager here, that's the data in the sweep, okay? So the first blob here will be the first angle of attack that you calculated with different iterations. Remember, we did 3 iterations, okay? So that's the first iteration, that will be the data for second iteration and the third. We always use the last iteration because that gives us the most accurate value, okay? So that's the first iteration, and then I go to my second angle of attack, which is, I think it's here. It's down here is 4 degree. Okay, again, I use the value here, 7 degree, 10 degree. So I would recommend you to start a new Excel file and copy and paste everything to the new Excel file and do the plots there. A lot better. And underneath here is your the lift distribution plot, okay, which is in the VSPAero here, is the load distribution, these plots, okay. What it will give you is your Y location, okay, that's the span-wise location, and then that's the each value here, okay. So drag coefficient, drag distribution, lift coefficient, lift distribution, okay. So the wing ID, the first ID, I think it's the left wing, okay. ID 2, if you go right, should be the right wing, and then left horizontal tail and right horizontal tail. I think if you plot them together, you should be able to regenerate whatever you've seen on the VSPAero, okay, these plots, okay. I think it's nicer to replot everything in the Excel, so it looks better in your report, okay. So after you finish analysis the data, there's one actually cool thing you can find in OpenVSP is the viewer. So if you launch the viewer, you will see, okay, this is the wing and horizontal tail of my airplane. I can actually plot, say, my pressure distribution of my wing at each angle of attack. So that's 1 degree. And then if we increase our angle of attack, that's 10 degree. Okay, it shows here. You can also plot your trailing wakes. So that's your wakes. And then again, here we can actually see if we plot the mesh here, because each red line is a vortex line. So that's how we calculate the vortex line, okay, on your wing. Okay, if we unshow that. And then if we increase our angle of attack to maybe 10 degree, you can actually see, when the vortices rolling up at your tip, which is really cool, and how the wing and your tail, interact with each other, which is also pretty cool. Okay, I would recommend you to first analyze the wing and the horizontal tail, and maybe if you finish that, you can redo it with your fuselage in there and vertical tail in there. Sometimes it might not run because of the nature of the complexity of the model. It might not run, but with the wing and the horizontal tail, you always run for most of the time and give you good results, and that's what you care about for most of the time in the aero performance of your airplane, other than the pure drag values. Okay, as usual, if you have more questions, please contact Sid and me if I'm still not graduated. And then having fun with the VSPAero.